Hi everyone, today what we are going to do is we are going to talk about PyTorch, and we are going to implement a simple image classification model with PyTorch. This is a part of our machine learning course, which is called Machine Learning ZoomCamp. So this is this course. Some of you might be taking this course right now. Some of you might be taking this course in the future. Some of you might have already taken this course. One of the modules of this course is deep learning, this module number 8. In this module, we use TensorFlow and Keras for training an image classification model. So the use case we have is fashion classification. So we have, where's this data set? This is the data set we're actually going to use. So we have different images of different types of clothes, like, for example, pants, shirts, shoes, and so on. So let's take a look at pants. So these are the images of pants. I collected this data set some time ago. And yeah, this is what we are going to use for implementing them, for creating an image classification model. In the course, it is TensorFlow and Keras. Now we're going to implement it in PyTorch, and also this will become part of the course too. So in the course, if you want to use Keras, you can use Keras. If you want to use PyTorch, you can refer to these materials, to this workshop, the thing we are doing today, to actually do this in PyTorch. All the links are already here in the description. So here is the link to the course. If you're watching this in recording, you can just go there. If you're watching it now, you can also go there and see this link. So this is the link to the course. The next one is linked to the workshop. So this is what I'm going to use to follow along the workshop today. This is what you can also use to follow along what I do. And then finally, we are going to use Google Colab, which is like Jupyter Notebook, but hosted. And a good thing about it, I'm going to now create a new notebook. And I'm going to call this notebook PyTorch ML ZoomCamp Workshop. What we can do here is we can actually have access to GPUs. And because we are going to train a deep learning model, we need to have powerful hardware. So for deep learning, we need to have GPUs. So there, to get a GPU, we can change runtime type. And here we have multiple options. So I'm going to stick to this T4, to select this T4 GPU. This is what we are going to use for now for this model. So, okay. What I will do today is I will simply show you the code. So I will not go into much of the theory. All the theory is in the course. So in the course, where is it? So this is the course. In the course, here I go into theory. There are some images, there are some illustrations. So if you want to understand some concepts that I'm talking about today, I will not go into details explaining them. You can refer to the videos in the course. In the course, I use Keras. So you can, if you're only interested in PyTorch, you can only watch the theoretical part that explains like different concepts and just implement things in PyTorch. I will also sometimes refer to the course and say, okay, this is how you do this in PyTorch, but this is how you do this in TensorFlow. Right? In TensorFlow, in case of TensorFlow, we use Keras. Keras is a high-level library, and PyTorch is a low-level library. So Keras is making things simpler, but here PyTorch is a little bit more complicated. That's why for sometimes for comparison, I will show, okay, that this is how we do it in Keras, but this is how we do it in PyTorch. Right? So that's the plan. So if you have any questions, you can drop them, you can leave them in live chat, but I'm going to start. Okay, and I'm going to start. So I will use this workshop document. And I'm going to start by getting this data set. So I already showed you this data set. So this is the data set with different images. And this is what we are going to use today. Right? So I'm going to clone it. So in order to do this, I just add an exclamation mark. Now I'm executing this bash command. And I have the data set. Right? So I can see, I think I can see the files here, right? So this is the data set. We have train, test, validation. And then in each category, in each part of the data set, we have different categories. So this is how our data looks like. Right? Because we use Google Colab, we don't need to install anything. So we already have PyTorch. So if I do import torch, we have it. Right? So we don't need to do any preparation. And typically, when you work with deep learning, in the course, we used anyways, like when you use any provider, like could be Saturn Cloud, could be maybe Amazon SageMaker, could be some other notebook, they typically have all these libraries installed. So you normally don't need to worry about that. But let's say if you have your local GPU, your local computer, like computer at home with a GPU, yeah, you would of course need to install PyTorch. You would need to install all the libraries we use here today. Why use PyTorch if Keras is a high-level library and PyTorch is low-level? Well, PyTorch is currently more popular for training models. Most of the transformers you see and hear, you see on social media, they are trained with PyTorch. So PyTorch is more popular. You see more content. Yeah. To me, if we're talking about simple deep learning models, doesn't really make much difference. Keras is much more compact and much more convenient. Also, for educational purposes, I still think Keras is better. That's why we are keeping the Keras content here. We are not removing it. I don't want to re-record the whole thing, but I just want to have an additional resource where we talk about PyTorch. So for many things, Keras is enough. Okay, so we will start with the simplest thing. Is we have some images, right? So we want to look at these images. And in Keras, yeah, you can see like there are some special built-in functions for that. In PyTorch, we don't have them. So in PyTorch, we actually use this pillow library that for actually in Keras, it's also used under the hood. But here we have to use it explicitly, right? So here is our pants. If we want to resize it to, let's say, 2024 by 2024, this is what we are going to use as input to our neural network. So this is how you resize it, right? And then when you want to turn it into an NumPy array, import NumPy as NP. So then the simplest thing you can do is just say NP array for this image. And then interesting. I did not know it's possible to do that. Yeah, so I guess it's a built-in feature for Colab. So this is how the data actually looks like. But because each thing here is a pixel with 3 values, right? Google Colab automatically translates it into an image. That's interesting. Okay, but this is how we get an NumPy array, and in this particular case, this is just yeah. So it just a bunch of. So I think this is what this shape is. Yeah. So we have height, width, and number of channels. Okay. So now we know how to load images. We want to create a deep learning model, or not create, but use. Right, so now let me just quickly check. Yeah, this is the, right now I'm talking about this Unit 3 using pre-trained convolutional neural networks. So we typically don't want to spend a lot of time. We don't need to spend a lot of time training models because somebody has already done this, and we can just take what the models they created. This is called pre-trained models. We can just take them and use them for our purposes. There are many different models, and the data set on which they trained is called ImageNet. So there are many different images, and these neural networks are trained on this data set, and we can just take this and use this. So I'm going to show you an example. In this particular case, we're going to use a model that is called MobileNet. There are many different models, so actually, so first we use PyTorch as the framework, and then there is a PyTorch, there is a framework called, or library called Torchvision. So this is a library for PyTorch, or that specifically focuses on vision, and they have pre-trained models. So if I do models, PyTorch models, we see what are the models, what are the pre-trained models, right? So there's ResNet, there is what? Where is the list? MobileNet. So there are many of them. So now we are actually going to use this MobileNet model. Which one is it in our case? I think it's V2, right? So this is like, here's an explanation how to use it. So I remember, okay. So this is what I wanted to see. So here's a comparison, like how you can choose this. So you can see accuracy of these models, number of params, and other things, right? So MobileNet is a very small model, this one, right? So you see the size is very small. So this is how you can also decide which model you want to use. And the reason I chose mobile is because it's very small, it's very fast to train, so we will not need to spend a lot of time now waiting for things, but it is also quite fast, right? And quite accurate, not only fast, but also quite accurate. So that's why we're going to use this model. So let me add a bunch of imports. I already have some of them. So we'll have models. And now we will load one of the models, which is this ImageNet model, right? And when I do model eval, it means that I am using this model for evaluation only, for making predictions, right? So there are two, let's say, stages. You can use a model for training, and you can use model for evaluation. Right now, we just use it for evaluation. Then we need to define some preprocessing. So this is the preprocessing that this model is expecting. It should be documented somewhere. So typically you find these preprocessing steps on the internet, where in the documentation, where you read about this pre-trained model you're going to use, right? So this is typically what the steps you want to use when you deal with this particular pre-trained model. So first, you want to get your image. So this transform things describes the steps you want to take in order to go from the raw image to something that you can put inside the neural network. So first you resize, then you take the central crop. So here we have this image. Let me quickly show it to you. So we have this image, right? So taking central crop means that I don't know if it's visible. Maybe I do it. Resize 356. Yeah, I wanted to do this. And then let me copy it and open Paint. It's not the Paint I wanted to open, but okay, whatever. So we have this model, or this, image, and taking central crop means that we take this of size, whatever. Right? So then, in our case, it will be an image like that. So this is the preprocessing that we do here. So we resize, we take the crop in the center, we turn it into, in this case, we call it tensor, but basically we do this thing here, right? And then normalize. So there are certain things we need to do. So let me just maybe show you how it will look like when I do this preprocess when I invoke it on image. Right? So this is, instead of having this sort of array, where we have this sort of data, what we have when we use this preprocess function is this. So this is what we will, this is what will go inside the neural network, right? So this is just the they divide by a certain thing. So the idea is that we want our data to be smaller scale. So instead of having a number between 0 and 255, we have a number between, I don't know, 0 and 1 something. So this is just how neural networks like their numbers. Okay, so this is, we need to do some preprocessing, and then we do the predictions. So I already, let me actually do this X preprocess image. And so that's our input. And then the next step, what we do is, why do we need to do this unsqueeze? Let's see. We can see what is happening when we do unsqueeze. So when we do batch T, shape, and if we do X shape, yeah, so what happens is we turn this into a batch, right? So we just, typically when we send data to a neural network, we don't send just one image, we send multiple images. We can send multiple images, like a batch of images. Here is just one image, right? A batch with one image. This is what this unsqueeze thing is doing. And then we make a prediction. So no-grad means we are doing this for evaluation only. So we already did this eval, but this is kind of similar. So it's not, we are not training a model, we're just using the model. So this is how our output looks like. And here, what we have is the shape is 1 by something. So here it means we have only one image, right? Because our batch contains only one image, and we have 1,000 predictions. So we have a number for each class. So there are many different classes, all the classes from ImageNet. So there are many of them, and some of these classes correspond to clothes. Some of these classes correspond to, I don't know, fruit. Some of these classes maybe correspond to, I don't know, objects like cars. Some of these things are pens, right? So then we can find what are the most likely cases. So here we're dealing with predictions, and when we get indices, it means that, okay, so here the class number 608 is the most likely class. The class is 834 is the second most likely class, right? And then so on. So what we did now is we ordered all these classes by probabilities, but we don't know the names for these classes. So for that, we need to get the names. So if we look at this document, image classes, can I see it? Yeah, so this is how it looks like. Right, so for each line, we know that, I don't even know what tench is, hammerhead. Okay, so these are the classes. So for each, so if we want to know what do we have on this picture, so we need to find line number 608, or maybe 609, right? And then, because here it starts with 0 and here it starts with 1, I assume. So then it's gene. should be genes, probably, I guess. But yeah, I don't know why it's a gene. Maybe it's just one part of the genes. Anyways, so this is the prediction. It says it's genes. I don't remember, was it really genes or just pens? But of course, we don't need to open the file and look at this. What we can do is we can just do this automatically. So with this piece of code that I'm going to use, we can see that the top classes are jeans, suit, cardigan, sweatshirt, overskirt. I mean, some kind of clothes, right? So I don't think it's jeans, I think it's just pants, but this is close enough, right? So when we need to make a prediction, sometimes we don't even need to train a model. There are already pre-trained models that we can just take and use them as is to make some predictions. Right, so there are already 1,000 classes, so probably our class is somewhere there, right? But these models, they are general purpose models. What if we want to just train our model to just predict the types of clothes, right? So if we do this, then our model should be better because it's more, specialized. So this is what we're going to do now. So we're going to take the model that we already have, and we are going to tune it slightly, adjust this model in order to use for us to just predict this type of clothes. So let me check. So we talked about pre-trained models. And next one, convolutional neural networks. So here I explain how they actually work. So I will not do it right now. So like here we have different types of layers. I will not go into theory, but now we will talk about transfer learning. So transfer learning is this concept when we take a model that is already trained and we're tweaking it slightly so it does what we want. So in our case, we wanted to predict the types of clothes. So let's do that. For that, let me check here when we talk about transfer learning. So the first thing we use from Keras is downloading data, right? So we get data from directory. And we already do some pre-processing. We say, okay, like take the files from this directory and apply some resizing. So make them 150 by 150 and make them in batches of 32, right? So this is what this code in Keras is doing. So this is Keras code. And then it also applies pre-processing function. So this is this part here, right? So this is the pre-processing function. We need to normalize our data. And this is what this code is doing. So now we need to redo this part, but with PyTorch. So in Keras, it's very simple, but with PyTorch, we need to write a little more code. So this is how what we are going to write looks. So let me copy it, and then I'll explain what's happening. So this one, I don't think we need. So we need to create a dataset object that, yeah. So here there are some things like a directory in which it lives, what kind of labels we have, what kind of classes. So while Keras is doing this automatically, we need to actually do this ourselves. So this is some code for doing that. So what this thing is doing is just we go through the files on the file system. We use this pillow library image to open it. And then we apply some transformation, right? So we specify this transformation function here to the image, and then we return the image and the label. So this is what the dataset class expects us to do. We just do this for our particular use case, right? And this is quite generic, actually. So you can use it for any dataset that uses folder-based alignment. But I mean, like we have a class, and then inside the class, we have all the images of this class. So this is pretty common. So we have this, and we can use that. So what we did here is we kind of implemented this, where is it? This image data generator, right? And this, like, it's two things. And once we have that, we can specify our transformations. So I already did this, so no need for that. So we say that our transformations are resize, turn this into tensor, and then normalize. Right. So we don't, here in this particular case, we don't need to resize and take crop. We just jump into resizing and then normalize. So the reason we were doing this slightly differently, because this particular model expects it, this particular transformation, but here we are fine tuning, so we're changing the model slightly, so we don't have to follow this exact transformation that we have previously, but still, when it comes to normalization, we use the same values here. So we don't need to train for too long. Right, so we have this, and then right now for train and for validation, I create separate transformations, but they are the same. So right now they are the same, but later we will change them. It's like here we have this preprocess function. So this is the transformation that corresponds to this preprocess function. Okay, and now we do this. So we say, okay, here's this our data set that we defined here. It lives in this folder. This one, no validation, lives in this folder. This is the transformation we apply. And then there is this thing called DataLoader that splits these things in batches. So it can shuffle our data set, because by default here we shuffle, and here we don't shuffle, right? So when we do for training, we want to go over all the files we have, and every time we go over these files when we train a model, we don't really care about the order. It's actually better if each time it's shuffled. But when we're doing validation, it's better that we fetch the files always in the same order. And so here we reproduce the same logic. We follow the same idea here. So we have the batch size and we have shuffling, and now we are going to actually create a model and then train it. So for that, we already know how to, we already created a model here, right? Here. But what I want to do now is I want to create a class for this. So this is how it will look like. And there are two methods here in this class. The first one is creating the model. I think I forgot an import here. So here we create the model, right? And when we create the model, we use the same model as previously, right? So this is the same model. Where is it? Here, MobileNet, right? So this is the same model. But then in addition to what we have done before, what we already did is, first of all, we freeze the base model parameters. It means we're not going to change these parameters. We are only going to train extra things on top of this model, but the model itself we are not going to change. We also did it here when we were getting the exception model. We set it to trainable equals false. And the reason we do this, we don't want to update them during our training, because when we update it, we may accidentally overwrite the model parameters, right? And then for us, we don't want to have this, because somebody already trained this model. The weights there, the parameters of this model are already optimal, so we don't want to break this accidentally. Right? And then the classifier, the regional classifier, is in this case the one that is outputting like one of these 1000 classes, we want to remove it, but we want to add then a custom layer that takes whatever output from the previous layer and then creates an output layer with only 10 classes, 10 things. So in our case, we have 10 classes. That's why the output layer is 10. Again, for theory, please refer to this video, Transfer Learning. There I explain all these things. Here I just want to show the code. Right? And when you watch, when you do the module actually here, the deep learning module, the right progression would be first you watch the Keras TensorFlow videos with theory, and then you come back, you go back to the PyTorch videos, or then you watch the PyTorch videos, because the theory will make sense. Okay, so we do this. That's the first part where we define our layers, right? And then the second part is where we say in which order and how these layers should be applied. So here we define them. We say, okay, we have this base model. Then we extract the features from this base model. So features are these things that, like everything before the last layer with predictions, right? Then we squeeze them using global average pooling. Right, and then finally we have the output layer that turns like this 1280 into 10, right? And that would be our final prediction. Right, and now if we just use the model as is, we probably can do this. Do we have an example? Yeah, so if let me actually do that. So now this is our model. So model to device means that if we have CUDA available, means if we have GPU available, then we send this model to a GPU instead of running it locally on a CPU. And now I can do model forward with our image, let's say. Yeah, it will not work because I need to give it a data set, right? Okay, we will see. So what I wanted to do now, oh, it gives a suggestion. Okay, let's see what the suggestion is. Okay, so what I did right now is I just generated a random image, right, of size 1, like it's only one image, and we get some predictions, right? But right now, this model we haven't trained it, we haven't showed this model, we have not shown it the actual images, so it needs to learn now. So the predictions it's making, and they don't really make sense because the weights that we have here, when we created this output layer, they are random, right? So that's why they don't make any sense. So what we want to do now is we want to train this particular layer. So we want to adjust the parameters of this layer such that the predictions we make, they make sense. And so now we are going to do this. And we're going to use an optimizer for that. So this is going to be an Adam optimizer. We use the same optimizer here, I believe. Yeah, it was Adam too. And then we use loss categorical cross entropy. This is for multi-class classification. This is the typical loss you use. Again, for theory, refer to this module. Okay. So this is our optimizer. This is our loss function. Now we need to train our model. In case of Keras, that's all we do. We just say model.fit. We say for how many epochs we do this, meaning how many times we iterate over our training dataset. And then finally, we also specify what is the validation set. Validation set where we evaluate our model, right? On which dataset we want to see the report, right? This is super simple in case of Keras. In case of PyTorch, it's a bit more complicated. So that's the code we are going to use now. So I'm going to copy it and I'm going to paste it. And I'm going to try to explain it. So I added some explanation, or I actually asked here in Colab, we have Gemini. I think there is a Zoom thing that doesn't let me show you. Okay, here, right? So here, Gemini, I ask, hey, Gemini, can you please add comments? And it did. So it's actually quite nice thing. And also, I didn't mention this at the beginning, but I think I should, that this code that we are going through now, it was also generated by Gemini. So what I did is I opened my notebook from the lectures, the one, I think one of the, we have notebook, this one. So I opened this notebook with Gemini, with Colab, and I asked, hey, Gemini, can you please translate it to PyTorch? And it did, and this is what I'm showing you now. Okay, so as you see, the code is a little bit more complicated. So this is what actually Keras is doing under the hood. But we don't see it because in case of Keras, we just see model.fit. Here we don't see this. So there are two things. First of all is we have the training phase. So this is the training phase. And we have the validation phase. So let me walk through with you through each one. Right? So first, we have an epoch, right? So this is, we want to iterate over the entire data set once. So this is an epoch. Then in each epoch, it consists of training on multiple batches. So if we take, I don't remember how much data we have, but let's say we have 1,200 files, right? If we split it into batches of 32, we'll have 38 iterations, right? So this is what we are doing here. So we are iterating over all the batches we have, and each batch is 32 or less, right? Because this is how we this is how we define our data loader, right? And what this what this train loader is giving us is it gives us the pictures and the labels for these pictures, right? So the pictures are already normalized. These are already 4-dimensional arrays or tensors. And then we have also labels, right? Then we send them to GPUs. Where is it? I lost it. And then we start optimizing. We say we make a forward pass. So we call this model.forward. Yeah, so I want to go into details of that, but what is happening right now here is we optimize the weight. So we make a forward pass, we make a backwards pass. And this way we adjust the weights of this layer. So we have this one layer that we want to train. And this is happening through backpropagation using this Adam optimizer, right? And this is what is happening right now, right? Yeah, so this is a bit technical. I don't necessarily want to go into details, but again, you can ask Gemini, or you can take any class about neural networks. There is one class I like and I recommend I don't know if I have a link here. It's Stanford Neural Networks Computer Vision. Yeah, this one, CS231 and Deep Learning for Computer Vision. If you want to understand what's happening in this code here, in this part, I suggest you take this course. I thought I opened it, because they explain this, and also you will have to implement, like when you do this class, you will have to implement this yourself. So you will need to implement backpropagation, forward propagation, backpropagation yourself. So I did this at some point. It's very educative. So I do recommend checking it. Yeah, so you will, when you do this, you will learn, you will actually know what's happening here. And then, so here we optimize. We do this for all the batches. And after that, so we do it for all the batches. After that, we report the loss, right? And after that, we have the validation phase, which is very similar. We except we don't do any gradient calculation. That's why we have this torch no grad. And then we again iterate over the batches in our validation dataset. But here we don't do the backwards pass, we only do the forward pass, right? So we just apply the model, and then we see if the, here's our accuracy. We see if the predicted labels, they match the actual labels. And this is how we calculate accuracy. So this is the calculation of accuracy. And then at the end, we report it, right? So this is our tiny function that in Keras is just that, but here it's a lot more. Well, to be frank, it's not fair to compare PyTorch with Keras, because PyTorch is a low-level framework and Keras is a high-level framework. It would be more fair to compare PyTorch with TensorFlow. So TensorFlow is a low-level framework too. And we don't use TensorFlow here. We use Keras. We use the Keras library, which is a part of the TensorFlow that makes interaction with TensorFlow easier, right? There are frameworks like Keras for PyTorch too, but I don't really know them. So that's why for me, like I usually just used plain PyTorch. But when it comes to TensorFlow, I rarely use TensorFlow, plain TensorFlow. I usually use Keras. But anyways, I think it's training. And we see the results here. Right, so we already did 2 epochs. And well, right now it's doing it, we asked it for 10. So this code, we are going to need this code again, right? So I don't want to copy paste this code over and over again. That's why what I'm going to do is I want to put this inside a function. So this function here it just includes all this code that we have, right? So the code we have here, it goes here just without comments, right? So that's the same code. Okay, so while it's training, let's want to see the questions. I trained the model with efficient B0 to classify subsea assets using ImageNet as weights, only to end up with an error. I mean, it's very hard for me to say, like, you would need to check what it is. So probably I see that it's 331 versus 333. So probably somewhere some dimensions get squeezed, which should not be squeezed. So I trained with RGB, which is 3 channels, but it kept reporting, which is grayscale. Right now, it's hard to help. I would ask the easiest thing to solve this is actually asking AI, right? So ask ChatGPT or ask, I don't know, Gemini here. So if you use Colab, using Gemini is so simple because you don't even need to leave this this window, right? All you do is just click on this thing. You get the window, like this sidebar, and you talk to Gemini. And usually, like, it's fairly good. Is this Fei I think this course, yes. This course, I already closed it. Was it CS2? Yes, this one. So I know, I don't know if, yeah, it's Fei I remember Andrei Karpaty was one of the instructors. But yeah, the main instructor is Fei A Colab free tier is enough for this module, yes, this is enough. You don't need anything else. Okay, I see that it finished. So what is the best accuracy we had? That was this one, 77, which is not bad. Okay, so what do we have next? Next, we tune the learning rate. So here we have this parameter, learning rate. It's a parameter for our optimizer, this Adam, right? And we want to be careful with this parameter. If we set it too high, then our model will, with each iteration, will override the previous results. If we set it too low, our model will learn too slowly. So it's like with XGBoost, in XGBoost we have this parameter called eta, I think, which is the learning rate. We need to be careful with that. And the best way to understand which parameter is the best one is just try multiple options and see whichever works best. So what we can do now is we have this. I'll actually create. I'll create a function called make model, and I think this is what I did here too. So let me actually go to the next unit, adjusting the learning rate. Oh, you have to watch this video. I spent so much time drawing these things. Yeah. So there I explain like what's the idea behind this learning rate. And there is a very nice analogy I used is the number of books you can read. So you can read a lot of books, but very fast. But then the question is how much you remember. Then you can read just a few books, but thoroughly, and maybe you can read one book very, very, very slowly, right? And this would correspond to different learning rates. Anyways, so here there is this function make model. So I'm going to create a similar one, and here, yeah, with learning rate. And actually, what I can do is I just copy paste it from here. Then we have this clothing classifier MobileNet model. Then we put it to CUDA. Then we create the optimizer with this learning rate, and then we return model and the optimizer. Right. So now we can have a loop for learning rate in I don't know this, and then we create our model, make model, and then we do train and do late. Okay, maybe we will also what we will do is print learning rate. Okay. So did I miss anything? I think I did not. So, but also I think we just evaluated this one. So as far as I remember, the best one was this one. So let's not. Model train, of course, yeah, it kind of. Model train, what? Wait a second. Model optimizer. Yeah, I don't remember what I was talking about. I think I was talking about the learning rate, so I think that was the best one. And I also don't want to spend too much time right now on training these things. Because it takes, even though we are doing this on GPU, this is a fairly small model. But yeah, I don't want to spend too much time. But this one should have an accuracy around 81%. Yeah, thank you, Damu. Optimizer is missing, was missing now. I fixed it. Okay, so I think we can just go to the next one. So the next one is we can add an extra layer here, right? So now we optimize the learning rate, but there are some other parameters we can optimize. And one of the parameters here is, okay, we have this output layer, but then we can add a layer, inner layer in between. So this could be a layer that takes whatever features from this base model. And yeah, so it would be something between this and this, right? So sometimes it can help, sometimes it cannot. Then what we can do is we can just test and see if it helps in our case. And I think here it would be, okay, wait, checkpointing. Okay, this is a bit, adding more layers. Yeah, that's the one. So we can add more layers. And again, why we want to do this, you can check the video, but here I just want to show you how we do this. Yeah, I'm doing things slightly out of order, but let me just do this and then I'll go back to checkpointing. So here we will add a new inner layer. Maybe what I will do is I will just copy this thing so I don't copy this all. And then how do I paste the cell? Maybe I just do that. Yeah. Okay. So I want to add this part. And then there's also this parameter, size inner, right? So I want to add it here. And then I want to add this thing, or actually, because I will also need to change the input size of this output layer. So you see, previously we had this, but now we will have this. Because the thing that we put inside our last layer changed, because this is the output of this layer. And the input to this layer becomes this, right? So we just squeeze in one extra layer between the final one and the output of the base model, right? So now this way we added one more layer. And of course, we need to add it here too, right? So let me do it here, right? So then we have this inner, then there is the activation layer between them. Again, for theory, you can check this video. And what else do we need to change? I think that's it, right? So we added these two things. We modified this one, and here we added these two things, and here we add an extra parameter. For this one, let me stop it. So I think you believe me that, yeah, you see, 83. So this is fairly good. And what we also see here is after we had 83 accuracy, it dropped, and then it dropped again. So, which is why it would be nice to save this particular model, right? And then, because later we overwrite this model. So we will do this now, and we combine this with this new model. So let me execute that. And so first, so this thing I talked about here is called checkpointing, right? So this is checkpointing means we see that this is a really good model, so we save the weight, because we know that later it may accidentally override it, or not accidentally, it's just as a part of training process, it can override it. So we better save this model because it's doing pretty well on our validation data set, right? So now let me take care of this part, and then we will also come back to checkpointing. Okay, so let's train this model. So how did we do this before? So before we had this make model function. So I'm going to also add it here, so then we can change these things at the same time. So this make model will have now two parameters. In addition to learning rate, it will have a size inner parameter, which we will just pass to our model. Size inner. Right. So this is, we're changing our make model class. And what I can do is I can just copy this code. And let's say we think that the best learning rate is this one. So we set it. And now we can iterate over size inner in, I don't know, something like this maybe, right? So these are the different sizes that we can try. And size inner, and then we just do evaluation. Yeah, let's run. Yeah, of course, I don't want to run it like for all three. And just to give you an idea how we actually do this. So if I wasn't doing it live, I would actually run all three, wait till it finish, finishes, and then also I would add checkpoints, so then I don't, if I accidentally discovered a good model, I would make sure I keep the weights, right? Okay, and Google Colab uses 2 spaces for indentation. I like 3, that's why I'll change it. Okay, let me stop it. So I think in my experiments, the parameters were this one, and learning rate this one. So now I'm going to just make a model and train it. But also I want to implement this checkpointing thing that I mentioned. In order to implement checkpointing, we will need to adjust our training function. Again, in case of Keras, this is actually pretty simple. You include a callback. I don't have a code. Yeah, here, model checkpoint callback. That is simply taking care of that. But here we will have to implement it ourselves. It's actually not that complicated. It's just the number of the amount of code we need to write is, yeah, I'd rather not write this code, but it's okay. So basically in our training loop, we always keep track of what is the best accuracy so far. And at the end of our loop, when we already report all the accuracies, we check if this accuracy that we get on this loop, on this epoch, is better than what we have seen so far. And if it is better, then we of course update this validation accuracy, but we also save it to this checkpoint path. So let's call it V2. I'll call it clothing V2, right? V1 was without the inner layer, and V2 is with the inner layer. Okay, so now let me, and I will actually, what I will do is I will take this function and move it slightly. So then like all the things are now in one place. So we have, I have the model, I have this make model thing, and I have train and evaluate in one place. And now, yeah, we don't need that. Now I am going to just run this thing. And we will see now when it trains, it will actually save. Why it's not showing anything? It will actually save things to checkpointing. Is something else running? Okay, it started. So of course, the first iteration we always save, because yeah, it's the first one. It's definitely better than things previously. And now we run it. We can run it, I don't know, for 50 iterations, and then one of them will probably be good. Would it be possible to inherit from the initial neural network and change its architecture? Yes, but you don't want to do this, because the initial architecture already is thought through. It already has weights, because somebody trained it. And if you change it, then you lose the weights, right? And you will need to, of course, maybe if your change is somewhere at the end, then it's okay. But if your change is at the beginning of your architecture, then you'll have to do all the training from scratch, right? You don't want to do this. You want to avoid it. Yeah, because somebody with like big GPUs already trained this model, so you want to just build on top of what they did. But if you are willing to train your model from scratch, then of course it's okay. It's possible to get the initial neural network and change its architecture. You can do whatever you want. You can. So here, when we define the model, here we have this base model, right? But instead of base model, what we can do is we can just have a bunch of these things, and then we can define architecture ourselves, right? And then we can see how this is implemented. I think it's actually possible to find it. Yeah, so we have all these models, MobileNet V2. So this is the model, right? And we see what we have. So we have this normalization layer, we have, oh, whatever. Like we have some things here. Yeah. So then technically what you can do is you can just copy these things and change it to whatever you want. Okay, what I saw is we already have a fairly good model. So what's next? I think the next thing that we do is dropout, right? So dropout is a way of regularizing your model. Again, for theory, check this thing. So there I explain what dropout is. But yeah, it's just a way to prevent overfitting. So while when we were talking about linear models, we use regularization in one way. Dropout is a different way of doing regularization to make sure we don't overfit on certain parts. So in this case, I think the thing I was talking about, that on this t-shirt we have this label, right? So our model, by seeing this image over and over again, might overfit to, if there is a label like that, then it must be a t-shirt. But in real life, maybe there is a hat with this label. And then, yeah, the model may accidentally think that this is not a hat, but it's a t-shirt. So dropout helps with that. And I'm going to add dropout now. And when we add dropout to our model, we need to train it for longer, because we add regularization. We make it more difficult for our model to learn, which is why we need to learn to let it run for longer, right? And then we add dropout here between this thing and this thing. Was it after hello? We add dropout, and we need a parameter drop rate. So drop rate is what's the percentage percent of weights that we drop at each iteration. So we mask them, the model doesn't see them at each iteration. So that's what we call dropout. So this is the percent of things we hide. And this could be, this is again a parameter that we tune. So we again make a loop. It's after hello, right? So we again make a loop. And in this loop, we try different parameters. Right? Like with everything else, we usually use validation set to actually optimize to find out what is the best value for this parameter. Drop rate. And then here in this, I'll put up a bit. But I will change it to version 3, because this is 3. Version number 3 will be with dropout, right? Of course, I probably want to make it configurable, right? I don't want to change it every time. And also, you probably want to have something like callbacks. But then if you implement all that, you'll end up with like a higher level framework yourself. Okay, so we have this make model. And here drop out, we can try, or drop rate. So we can try values like 0.1, 2, 5, and maybe 0.7. So this is pretty, how to say, hard regularization, because we're making it super hard for the model to train. We're hiding 70% of the image or 70% of the weight for the model. So we're making it super hard for the model to train. Size inner, let's say 100. Drop rate, drop rate. But also number of epochs should be higher because we introduced drop rate. So now we should train not for 10 epochs, but at least for 25, if not for 50, right? Especially for this one. So for this one, we need to iterate many, many times. Here. So I will not do it for like all these weights. This is something you can do as a part of your homework to make sure that this is actually the best parameters. But as far as I remember, 0.2 was a reasonable drop rate. So let's just, I'll kind of pretend we are optimizing the model here. We're optimizing different parameters. But in practice, I'll just, use this 0.2, I think. Okay. So now we talked about drop rate, dropout. So here again, you can learn the theory about that. And the next step, data augmentation. So this is a different form of regularization. So dropout is one way of regularizing your neural network. You're just hiding parts of that neural network or the parts of the image. And this way you make sure it doesn't overfit. Another way would be what we call image augmentation or data augmentation from the images that we train, because we know that, let's say I want to create a model that is, let me, I don't see my, can I see? A second. Maybe I stop sharing the screen for a second. So I have this jacket, right? And in pictures, maybe all the jackets are like that. They are properly placed. But in our train set, maybe the jackets are rotated or whatnot, right? So we need to be... so when we see this happening in our validation set, but we don't have this data in training set, we can augment our training data set. We can generate more data for our training data set. And these things we can actually do programmatically. We don't need to take more pictures from different angles. What we can do is we can just rotate the regional data set, or we can, like, there are many, many different augmentations we can do, or transformations to the data that we can do. This way, we kind of generate more data from existing data, right? And this is a form of regularization, because this way our model will not learn that, I don't know, the things are always properly aligned vertically, right? So they can be moved around. Or they can be, you can see here, right? So different transformations you can do. So what kind of transformations we can do? Rotation, flipping. So for example, flipping, it's like mirroring, right? Zooming, random cropping. Random cropping is when we take a picture. This is what I think I was showing you here, right? So here, maybe what we can do is, first of all, we can rotate our image, right? So wait a second, we can rotate the image, right? And then we can crop this part and use this part for training. Then next time when we rotate it slightly different. And then we crop maybe this part, right? And then we know that it still pans, right? And for each epoch, our augmentation is different. We look at the same image, but we apply different values for this augmentation. We rotate it to random size. We flip it randomly. We stretch it. We shrink it, like whatever. Right. So this is the idea behind augmentation. Let me stop this thing for now. And in Torchvision, we have these different augmentations. So we can have rotation. So here we would rotate up to 10 degrees. We would zoom in or out. We would randomly flip horizontally. And of course, when selecting the augmentation, you need to think does this augmentation make sense? Of course, you can go crazy with all sorts of augmentation, but then at the end, it also makes it more difficult for your model to learn things, right? Like with Dropout. So then when you select augmentations, you also need to be thinking, okay, like does this augmentation represent the data we might have in our test data set or not, right? So this is something you also need to think, yeah, when doing this. And again, when we do this, we only apply it to training data. We don't apply it to validation. So validation data stays the same. So we don't apply augmentation to validation data set. And the reason we don't do this is if we start applying augmentation to our validation data set, it will become not deterministic. We want our validation set to be deterministic. And we want to be able to use it for comparing model number one, version number one with version number two, with version three, right? And if we now introduce augmentation here to validation data set, we will not be able to say that this 80% is better than 80% of model version 3, right? So that's why we keep the validation data set intact. We don't transform it. This gives us a way to, this makes it possible for us to compare it to previous models, right? And also, yeah, we don't have any randomness. So then we can also compare different runs. So we know that, okay, the next batch, it actually did improve, right? If we introduce random augmentations, we are not sure. Yeah, that's why we do it here. And I stop it, right? And so this is when we have this loaders, right? So this is when we have augmentations. So let me go all the way up, even here, and then I can replace this one. And then I would need to do this one. And what I do now is I simply, so maybe let me make it V4. This doesn't change, right? Because augmentation is something we do to data, not to the model. And I will just do drop rate 0.2. So I will remove this thing. Okay, and let's try. Did I forget something? Yeah, come on. Right. Okay, why I have two of these things? Let me delete this one. Okay, so now we added data augmentation, and let me see what I have here. So yeah, just a few more things. So first is how, now we save the model, how do we load it? So let it run, let it maybe for, I don't know, for a few epochs. And in the meantime, I'll check the questions. Can we see network tree like scikit-learn and topology? Simple should usually. Sorry, I don't understand it. Like, I guess your question is whether you can see all the, visualize the architecture of the neural network. I am not aware of that, so maybe we can ask Gemini, right? Can I visualize the architecture of our neural network? I'm pretty sure there are frameworks that look at your class, at your model, and they build some sort of visualization. Because for us, yeah, torch summary, okay. So while this thing is running, I don't want to execute this. But yeah, it looks like it's possible. But yeah, I guess when you look at the forward path, it's kind of clear what is the sequence of steps. So from that, maybe you don't even need to have this visualization. But of course, the code can be messy. You know what? I think this model is good enough. This one, V4. Of course, if we train it for 50 epochs, I'm pretty sure that at some point we will hit somewhere near 90% towards the end of training. But I'm going to just stop it. And I'm going to give this one a try. Okay, so it already has Torch summary. We don't need to install it. I don't know if it's useful, but this is something we can do also in Keras, right? So this is indeed visualization, but more like textual visualization. So this part is MobileNet. So this part from here till here is MobileNet, and this is ours. Right. Okay. I don't know if it helps, if it answers your question. Yeah, what I had in mind is more visual than that. But yeah, I think this one is also quite helpful to understand. Okay, please analyze. Yeah, I don't know what it's doing. All right, it just provided a summary. Okay, cool. I'm not going to read it, but then I will share this link with you, so then you can actually do this. For now, please go away. Because what I want to do now is I want to take a look at how we download this. So I'm going to take this thing. Okay, and I want to see how we can load this model. So that's our model. Thing size inner, I think we had 100. Drop rate, this one. Number of classes, this one. Right. Then this is our path. And now, yeah, let me just do this. So this is our path, and at the beginning, remember we were applying this to our model. So let me put everything together. And want to execute this one more time. At the end, yeah, I don't know, should I remove it? Oh, yeah, okay, we can let it stay. I can hide it, right? Okay, good. So now I want to pre-process it. I think we have this validation pre-processing validation transform, right? Then unsqueeze, then apply. To device. I think that should work. Okay, so what it means, what this thing means is the model, the class number 4 is the most likely one. Then class number 7 is, maybe we don't even need to sort, like why do we need to sort? So let me just take a look at the output. And then with the output, we can see these are the scores for different classes, and the class number 2, 3, 4, 5, or number 4, like with index number 4, this is the most likely one. I think it's pens, but probably we need our data loader to find out, right? Where is it? So we have this clothing dataset, right? And here, train dataset. So what do we have here? Cluster index, right? So number 4 is pants. So what we can also do now is we can, let me turn it into a list. So these are our classes. And this is our output. So number 0 to CPU. Can I turn it into array? But I think what I can do now is zip classes output. And then I turn this into a dictionary. Okay. I mean, I wanted to have, maybe I can do the list as a list. Yeah, or whatever. You get the point, right? So now what we have is that for the class pants, this is the highest value, right? And then finally, what we will need to do for the next module. So in the next modules, after this deep learning one, we are going to talk about serverless. In this module, we are going to talk about using these models with AWS Lambda, right? And we already had a workshop. This will be a part of the course too, this serverless workshop. And there I show how you can, with Lambda, you can serve deep learning models, also using ONNX. ONNX is a special format that you can train a deep learning model with TensorFlow, you can train a model with PyTorch, you can train a model with ImageNet, and then you can save it to ONNX, which is platform or framework independent format. And then you can use ONNX serving to actually serve your model. So the last thing I want to show you today is how we can export to ONNX. And it's actually pretty simple. So this is what you do, right? Yeah, I mean, of course, you kind of probably need to understand what to put here, but it's always input, it's always output. Yeah. So then if I do something like that, module ONNX is not installed. Okay, so how about we install it? Pip install ONNX. And then I save this model. Okay, there is a new one. Okay, that's a lot of text. Yeah, if you feel so inclined, you can go through this, but this is how we can save our models to the ONNX format. Now we have it here, and now we can use it in the next lesson when we serve our model with serverless with AWS Lambda. Okay, that's actually it for today. So as I said, this is going to be to become a module in the course. And the way you watch this module is first you watch the theory. So you first watch the existing content where I use TensorFlow and Keras. You learn the theory and then you watch this video to understand. If you want, of course, if you want to learn PyTorch, you can watch this video to understand how things you learned in Keras and TensorFlow, how they translate to PyTorch. There's more code, but PyTorch is more common these days, so a lot more people use PyTorch. So it has higher adoption in the industry. So it helps to at least understand how PyTorch works. But again, I don't think it's too different. And at the end, if you know concepts, that you implemented in one framework, you can always switch to another framework and do it there too. So, but here, the purpose of this workshop was to show you how to do these things. PyTorch. And that's actually it. So I hope you had fun. I don't see any questions. So the links are all in the description, and have fun with the course. So I'll be switching off.